Let's start the second part. So Noah Weninger is a PhD candidate in the Department of Combinatorics and Optimization at the University of Waterloo. His current research is on the design of exact and approximation algorithms for bi-level discrete optimization problems, with a special focus on interdiction games. Previously, he completed his master's degree in computer science at UBC on approximation algorithms for unsplittable flow problems. He is interested broadly in combinatorial optimization problems, game theory, knapsacks, graphs, and Matroid. Thank you for accepting our invitation, Noah, and please go ahead.
Yeah, thank you very much for inviting me and for organizing this excellent webinar. So this work is joint with another student at Waterloo, Amir, and also my PhD supervisor, Ricardo. So we're going to consider a special case of what we saw in the previous presentation. So in a binary interdiction problem, the general structure of the problem is that the leader is able to force the follower to set some variables to 0. So this is enforced by this constraint here that says y is at most 1 minus x. So if xi is equal to 1, then the corresponding variable yi must be set to 0. And the choice of these interdicted variables is constrained by a knapsack constraint. This C transpose X is at most C. And the objective is to make the follower's optimum as bad as possible. So it's a zero-sum game. The leader wants to maximize the follower's objective, and the follower, of course, wants to minimize their objective. So the specific specific interdiction problem I want to talk about today is shortest path network interdiction. So in this problem, we're given a directed graph, some source node and target node. We have an interdiction budget C, and every arc in this graph has some length and some interdiction cost, and everything is integers here. So writing this as a bi-level integer problem looks like this. So in particular, the follower's feasible region is going to be the set of indicator vectors of ST paths in the graph. And if the leader decides to interdict some variable, so if they set xe equal to 1, that means that every path that uses arc E is forbidden. So the objective is for the leader to maximize the shortest ST path length in the graph. So just to go over a quick example of this, make sure it's clear. So here we have an instance, and I've labeled the arcs with the length of the arc. And in this example, the leader can interdict any single arc. So the shortest ST path in this graph is this blue line here, and it is length 2. But an optimal solution for the leader could be to interdict this edge from A to T. And if they do that, of course, they block the shortest path. And so the optimal response for the follower is to take the shortest path, which is disjoint from X, which is this green path here, which has length 3. So this is a very classical interdiction problem. There's been some variants of it studied since the 1970s, and this sort of full generality version that we consider today was first studied by Wood in 1993. So it has lots of applications like infrastructure protection, urban planning, counter-trafficking. And this problem is NP complete even for unit interdiction costs. And because today I'm going to be talking about exact algorithms, I want to go a bit over the history of exact algorithms for this problem. So the most well-known baseline approach for it is the Israeli Wood-Benders composition from 2002. And this is practically a very fast algorithm. It can solve instances with like millions of of edges in some cases. And another approach that you can take is you can reformulate it as a single level mixed integer program, but this requires some big M constraint. And so it has a loose LP relaxation and is practically not very fast. You can also solve this with generic bilevel solvers like MIBs. But as far as I know, these are not really competitive with the Israeli wood approach. And potential reason for this is that the high point relaxation is trivial for interdiction problems because they're zero sum. So in this case, the high point relaxation is just the longest path in the graph, which is not very informative because the leader might only be able to interdict a few edges. And so just taking the longest path could be arbitrarily far from optimal. And there's also some recent works that have presented improved algorithms, and they're mostly focused on this case of sparse graphs. So very, very large graphs, but very sparse with small interdiction budgets. So in this talk, I'm going to present an enhancement for the Israeli wood Bender's decomposition. And we're focused on improving performance for very large, very dense graphs with large interdiction budgets. So this is something that, to the best of my knowledge, is not really addressed by prior works. So first, I'm going to talk about what the original algorithm is, then go over the enhancements, and then some computational results. So first, we need a little bit of notation. So we're going to let G minus X be the graph G, but with the arcs that have XE equals 1 deleted. So this is like the interdicted graph, essentially. When you delete all of the interdicted edges from G, you get G minus X. And we're also going to let SP of G be the shortest ST path length in a graph G. So now we can reformulate shortest path interdiction as follows. So we are maximizing over all interdictions X subject to the interdiction budget. And we're trying to maximize the shortest path length in G minus X. So the Israeli wood Bender's decomposition works as follows. Well, they present multiple forms, but this is the one that we're going to consider today. So the idea is that we maintain a set S of shortest paths in various graphs G minus X, so for some choices of X. And we're going to let L of S be the longest path in this set S. And so the algorithm works as follows. Initially, S is the empty set, and then we repeatedly solve these two problems, the master problem and the subproblem, and we stop whenever the master problem becomes infeasible. So the master problem says, find some X subject to the budget such that X interdicts at least one arc from every path Y in S. So that's what this constraint is saying. It's X must cover every path in S. So we find this X, and then the subproblem is to find a shortest ST path of G minus X, and then add this to S. So the set S is growing, and eventually we get to a point where there's so many paths in it that the master problem can't be solved because we can't possibly cover all these paths within the budget, and then we quit. And we can conclude that it's optimal. So how can we do that? Well, I can't really get into the full proof. It's not that hard, but the algorithm maintains the invariant that the longest path in S is at most the optimal value of the problem. And also when the master is infeasible, the longest path is an upper bound on the optimal value. So when we terminate, we're guaranteed optimality. Okay, so now for our enhancements to this algorithm. So our enhancements are based around this dual problem, which is known as the min-cost blocker problem. So we can define this B of t for some threshold t. So this is going to be the minimum cost x, such that the shortest path in g minus x is at least of length t. So why is this a dual to shortest path interdiction? Well, it's because we can reduce the problems to each other in the following sense. So the optimal value of the shortest path interdiction problem is going to be the maximum threshold t, such that b of t is within the interdiction budget. So all of our enhancements are based around relaxing and restricting this this min cost blocker form b of t, and then we solve this optimization problem over t to recover bounds for shortest path interdiction. So first, we need to define the notion of a detour. So I'm going to define the detour of some arc E to be the shortest ST walk through E. So in this example on the left here, E is this red edge at the bottom, and the detour through E is going to go from S to M to U to V to M to T. And so this has length 5. And it's important to note that this is not a path because it visits M twice, so it's a walk. But all paths are walks, so the detour of E lower bounds the shortest path length through E, which is NP hard. So we use the detour as like a proxy for the shortest path length through E. And if you look in this example, the shortest path through E actually has length 6 because you have to use either this edge S to U or V to T in order to avoid going through M twice. Okay, and the reason why we need this is to define this graph G of T. So G of T is G, but restricted to arcs that have detour at most T. And the key takeaway from this is that every ST path of length at most T lies in this graph G of T. However, there may also be some longer paths, but at least we're guaranteed that every short path is in this G of T. So we use this to get a polynomial time lower bound, or a heuristic, basically, on shortest path interdiction. So the idea is that we're going to restrict B of T to those X which are ST cuts in G of T. So why does this work? Well, if X cuts G of T, then X must cover all ST paths of length at most T. So therefore, the shortest path in G minus X is greater than T. And so we can conclude that the minimum cut of G of T is an upper bound for B of T. And now by this same reduction we use to get from B of T to shortest path interdiction, we can conclude that maximizing the min cut of G of T over all T, maximizing T such that the min cut is at most the budget C. This maximization gives a lower bound on the optimal value of shortest path interdiction. And crucially, this is polynomial time because the minimum cut of G of T, this quantity, which is represented by this blue line here, this is monotone in T, and so we can binary search to find this lower bound. Okay, and so that was based around restriction of B of T, but we can also consider relaxing B of T. So we can write B of T in the following way as an IP where we want to minimize the cost of X such that X covers all ST paths with length less than T. And if we relax integrality of this IP and then take the dual, what we show is that this dual can be reformulated as a length-bounded flow problem, which is something that's been studied previously. And analogously to in the previous lower bound, if we binary search over T, then we get an upper bound on shortest path interdiction on the optimal value. So how do we solve this length-bounded flow problem? So it uses the notion of a layered graph. So it helps just to look at the example, I think. So we have two paths in this graph, one from S to A to T and one from S to B to T. And what we do is we explode this into a layered graph where the layer number encodes the length of the path so far from S. So both A and B can be reached from S with an arc of length 1. So these, like this first blue arc maps to this first blue arc here, and it ends up in layer 1. But then the arc from A to T has length 1, so it goes from layer 1 to 2. But the arc from B to T has length 2, so it goes from layer 1 to 3. So by exploding the graph in this way, we can then restrict it to layers only 0 through T, and then only paths of length at most T are going to exist in this graph by construction. And this graph has pseudo-polynomial size, but we can solve the length-bounded flow problem by formulating an LP over this pseudo-polynomial sized graph. And so by binary searching over that, as I mentioned before, we get an upper bound for shortest path interdiction. Okay, so next, how do we use these ideas to enhance the Israeli-Wood algorithm? So the first thing we do is we use the lower bound. So what we can do is on each Bender's iteration, we consider the residual graph, so with x deleted and with the remaining amount of interdiction budget, C prime. And we compute this lower bound as mentioned previously. And then what we can do is if we decompose the maximum ST flow of this residual graph at with only restricted to arcs with detour at most LB, we can decompose this into shortest just into ST paths, and this is an idea that was presented previously in a different context. And if we decompose it in this way, then all such paths which have length at most LB can be added to S. And so this gives us a way to add multiple paths that we need to cover on every iteration of Bender's. And this is this enhancement is most effective on dense graphs because they have many disjoint ST paths usually. And so this can allow us to skip many iterations of Bender's. And the second enhancement that we do is we add two new heuristics for the master problem. So in the original Israeli-Wood algorithm, they tried using a greedy algorithm to try to find the try to find a valid solution for the master problem. And then if that fails, then they fall back to just running in an IP solver. So we add these two new ones. We first try a cut cover. So basically we consider the union of all of the paths in S, consider this graph. And now if a minimum ST cut of this graph has cost at most C, then we can take it, and that's a valid solution for the master problem. And then the other new addition is this LP-based heuristic. So the idea is we solve this length-bounded flow LP on this layered graph, but we restrict it to arcs that are in the set S. And if the results of this is integral, which it happens to be in many cases, especially on dense graphs, then it's a valid solution for the master problem. And in practice, we solve this using like a cutting plane approach, which avoids the pseudo-polynomial blowup in most cases. So if all of these heuristics fail, then we fall back to using an IP solver. So now I can present the computational results. So we consider three classes of instances. So we have dense graphs, so these have up to 2,000 vertices, around 2 million arcs. Sparse graphs, these have up to around 500,000 vertices, 4 million arcs. And we also test against the original Israeli Wood benchmark, which is these grid graphs. And we use very large interdiction budgets. So the largest interdiction budget you can set without the problem becoming completely trivial, because the leader can just disconnect the graph, is going to be the min cut -1. And so we consider these four possible fractions of the min cut -1. And yeah, so it's implemented in Rust, use Groby, single threaded, and a 1 hour time limit. So what we found is that the improved algorithm solves all 496 instances, whereas the original times out after an hour on 20 of them. And in this performance profile here, you can see that the improved algorithm is often 10 times faster or more. And at worst, is like maybe, well, I guess at absolute worst, it's 10 times slower, but like usually it's usually it's much faster or just a couple times slower in the worst case. So we see the biggest improvements on these dense graphs. So here's the comparison. So you can see that the improved algorithm took only 32 iterations on average compared to 191 for the original. And on average, it took 51 seconds compared to 478. So the improved algorithm is faster on around 91% of these instances, and the speed up is up to around 300 times. And we also see that the improvement is, it's even larger improvement when the budget fraction is larger. So these are the hardest instances where you have the very, very large interdiction budget. The improvements don't always help because on very sparse graphs, the overhead of computing the enhanced bounds outweighs the actual gain from them. So on these sparse graphs with low degree here, we see that we have much reduced iteration count, but on the very low degree ones, the original is a bit faster because it doesn't have to compute these additional bounds. And in particular, this is the original grid graphs that were tested by Israeli Wood fall into this very sparse paradigm. So it's kind of a wash on those ones. So we're not really any faster on those. So thanks for your attention. So for some future work, we're interested in extending this to partial interdiction and more generally to network flow interdiction. And it would also be interesting to combine with other improvements that have been published for the case of sparse graphs. So yeah, thanks for listening, and I'll take any questions.